Welcome back, everyone. I'm Jordan Giesecke, and this is The Limiting Factor. This is part 14 of the Lithium Mine to Battery Line series to break down and understand what was unveiled at Tesla Battery Day. This video is the second half of a two-part series on Tesla's lithium clay plus salt extraction process. The first video covered Tesla's strategy surrounding lithium clay, and this video will be more technical. Lithium mining is far from my core expertise in batteries, and this shouldn't be considered a deep dive. But I can shine some light on extracting lithium from clay to provide a base level of understanding. Before we begin, a special thanks to my Patreon supporters and YouTube members. This is the support that gives me the freedom to avoid chasing the algorithm and sponsors, and I hope will eventually allow me to do this full time. The links for support are in the description. Back to lithium clay. Lithium clays are found in valleys where lithium and lithium-bearing minerals have been washed out of the surrounding hills and incorporated into sediments such as clay. From what I can tell from photos, the clay in Nevada is typically hard, dry, and rock-like but friable. Friable means that with some pressure the clay will break apart and crumble. Lithium clays are being explored in the US because large portions of the western states, like Nevada, have lithium clays in abundance. There are no examples of a large-scale and fully operational lithium clay mine, but several are under development. If lithium can be extracted economically from the clays, the US won't need to import lithium. This may make the lithium clays vitally important to the US in the coming decades, possibly centuries. Let's start with what we know from Tesla Battery Day and work from there. Tesla stated that the process was to mix clay with salt, put in water, and the salt comes out with lithium. Other attributes were that Tesla's process is environmentally friendly, the specific salt was sodium chloride, all the elements were reusable, and the dirt would be removed and put back. Not all lithium clay deposits have the same chemistry. Even on the same plot of land, there can be many different chemistries depending on the specific location and the depth that the sample's been taken from. We'll assume that Tesla's clay resource will be extracted using the same process and on the same piece of land. To get a better understanding of the differences between lithium clays, we need a general understanding of how they're structured at the atomic level. The lithium in lithium clay can be held in two places, in the framework layer or the interlayer. If the lithium is contained in the framework layer, it's more difficult to extract because the lithium is actually part of the crystal structure. If the lithium is contained in the interlayer space, then it's much easier to remove because it's not contained within a crystal structure. These crystal structures are not all identical, and the specific chemical makeup of the crystal structure can dictate the extraction process. The framework layer can include elements such as lithium, magnesium, aluminum, silicon, and oxygen. The interlayer can include positive ions such as lithium and magnesium. The basic question to ask here is, if the target element is lithium, what unique characteristics does lithium have compared to the elements around it? For example, enthalpy of hydration, atomic radii, and charge states. By identifying the unique characteristics of lithium versus the other elements in the ore, and then developing the engineering required to select for those characteristics, we can engineer a process to knock the lithium out of the clay. In other words, it's hardcore chemistry, and we'll take a more pragmatic, tool-based approach today. All the other elements surrounding the lithium are called gangue. Lithium clays are typically greater than 99.7% gangue. This means that extracting the lithium is just a small part of the challenge. The rest of the challenge is separating the lithium from the gangue and returning the soil to the earth in a non-toxic state. Furthermore, this all has to be done economically at a scale of hundreds of thousands of tons. If you combine the complexity of the chemistry with the nearly infinite variability of the lithium clay material, it means that doing an actual deep dive on what Tesla's process could be would provide enough material to start an entire YouTube channel on the topic. Given the huge variability in clay resources and the extraction processes, we need to take a pragmatic approach to understanding Tesla's potential lithium mine. We need to look at the basic tools that could be used in each step of the process, from clay to lithium hydroxide, and how they fit together. The image on screen is an illustration of some of the potential major steps that could be used to extract lithium from clay. This type of process diagram is called a flow sheet. My flow sheet shows what's being done to the raw material in red and also what tools can be used to do that in gray. The steps in the red boxes are words that I've chosen, and some are not mining terminology. I've structured the illustration in a way that makes sense to my mind, and it's a distillation of the dozens of flow sheets that I've reviewed. Earlier, I suggested that lithium hangs out in two places in the clay: within the framework layer, where it's part of the crystal structure, and within the interlayer, where it's not part of the crystal structure. Let's look at what Tesla's process could look like for each of these, starting with lithium in the framework layer. I emphasize could here because these are wild speculation. The first step in the framework layer process is to mine lithium. With a lithium clay, this would be pretty straightforward and could probably be done with an excavator and dump truck, so I haven't added any detail in the gray box. The second step is where the material is atomized, or broken down into smaller pieces through crushing, grinding, or milling. Atomizing the material makes it easier to move around and work with in later steps. With clay, atomization would be easy because it's friable. The third step, separate, is optional. Any mined material is a mixture of the valuable material being mined and gangue, or waste material. In some cases, the valuable material has a different density, solubility, or particle size than the rest of the material. If that's the case, a lot of the gangue can be removed at the separation stage at low cost. This step can also reduce the volume of material that's processed in later steps, which saves even further cost. If Tesla's lithium clay has any unique characteristics that allow some of the gangue to be removed at the separation stage, Tesla will do this. Next, the denaturing stage. By denaturing, I mean breaking down the crystal structure of the lithium clay. This is typically done with heat or acid to release the lithium, but Tesla said they would use an acid-free process. An alternative to acid and heat is to denature the clay with table salt and heat. The clay plus salt mixture would be roasted at a temperature of around 1000 Celsius, where the salt would become highly reactive and denature the clay, releasing the lithium from the framework layer. Salt costs about $60 per ton, so it's extremely cheap. Although the energy cost would be high, Tesla is an energy company and might be able to generate this electricity at very low cost. The soak stage involves exposing the lithium clay to a water solution. This can be done in situ, which means pumping water through boreholes, in a tank, or by heaping the lithium clay on a rubber mat and spraying it. Tesla would probably use a tank to reduce water loss and wastage, which is important in the desert. The soak solution would dissolve metal salts from the roasted clay, such as lithium chloride, magnesium chloride, and sodium chloride. However, it would be mostly clay, which brings us to clarification. The soak solution at this stage would look like muddy water, but it would have lithium dissolved in it. I haven't seen an explanation of how the muddy water could be clarified in the flow sheets I've seen, and so I did some general chemistry research here. This turned up microfiltration, precipitation, and centrifuge processes to separate the clay from the lithium. Precipitation seems the most likely here. Clay is typically a colloid in water. Colloids are charged, extremely fine particulate that doesn't sink or settle out of solution. The charge causes the clay colloids to repel each other rather than clump together and sink. Those clay colloids could be precipitated out of solution by a flocculant, such as aluminum sulfate, aka alum. Alum disrupts the negative charge of the clay particulate, which causes it to clump together and then settle out of solution. It's often used by municipal water supplies to remove colloids from water, so it's a cheap, common bulk material. The precipitation removes the clay from the water, making it clear rather than cloudy, which is why this step is called clarification. The clarification step leaves us with two materials. First, the clay that's precipitated to the bottom of the tank. I'm hoping that clay would be in a relatively benign state from an environmental standpoint. I'm probably going to regret this question, but if anyone out there knows a thing or two about flocculation, let us know in the comments below. The second material we're left with after clarification is an aqueous solution that contains a mixture of dissolved metal salts. These salts could include lithium chloride, magnesium chloride, and of course the sodium chloride that was added to extract the lithium from the clay. but the salt we're most interested in and targeting for extraction is lithium chloride. In other words, what we have after the clay has been precipitated out is a dilute lithium brine. This brine would be drained into another tank to undergo extraction. There are two ways to extract the lithium from a brine where the water could be recycled. The lithium can be removed from solution with direct lithium extraction, DLE, or use chemicals that react specifically to the lithium and cause it to precipitate out of solution. DLE is a process where lithium is pulled directly from solution, and it can be done in several different ways. It hasn't been used at large scale for lithium extraction yet, but it's very close, and it appears that it will start scaling massively in the next 5 years. Let's assume Tesla uses both a DLE and a chemical process here. A DLE adsorbent would extract lithium chloride from the brine solution. This would leave a lithium chloride-coated adsorbent and a solution of sodium and magnesium chloride. The sodium and magnesium chloride would be drained away. We'll refer to this as the waste brine. The waste brine would have to be run through several more steps to convert it back to water and dried salts. The water and dried salts could then be reused in the process. This just leaves us with the lithium chloride-coated adsorbent, which would be flushed with a solution to release the lithium chloride into solution. That lithium chloride solution would be drained away to another tank for the second extraction step. In the second extraction step, the lithium chloride brine would be reacted with sodium carbonate, which would precipitate lithium carbonate from the solution. The water would be drained off for reuse, and the remaining lithium carbonate slurry would be dried to a powder for the conversion step. In the conversion step, the lithium carbonate would be reacted with lime to form lithium hydroxide, which is the final product Tesla would need for its cathode factory. Finally, remediation. The difficulty at this stage completely depends on Tesla's process. If, as I suggested above, they use a basic flocculation process that's used in municipal water supplies to precipitate the clay, and the metal salts don't precipitate with the clay, it might be relatively easy to return the clay back to the environment. I imagine it would be more complicated than I'm suggesting here and involve a significant amount of environmental assessment. Overall, the process I've laid out here for extracting lithium from the framework layer would be energy intensive, complex, use large amounts of chemicals, and would only extract about 30% of the lithium from the clay. What could the process look like if lithium was contained in the interlayer and was capable of being pushed out relatively easily? To make a process like this work, Tesla might have to extensively search for just the right type of lithium clay. The lithium in the clay would have to be capable of freely exchanging lithium in the interlayer with sodium in the table salt in a process called cation exchange. For this process, we'll use advanced technologies that haven't been tested at a production scale. Tesla starts by mining, atomizing, and then separating the material with a process that's optimized for their lithium clay. The denaturing step would be skipped because the crystal structure wouldn't need to be destroyed to release the lithium. In the soaking stage, the atomized and separated lithium clay powder would be added to a tank where it's mixed with a saltwater solution. The lithium in the interlayer has a stronger attraction to water than sodium in the table salt. This means that under the right conditions, some of the sodium from the sodium chloride might swap places with the lithium, releasing the lithium into the solution. However, some magic would be needed here to accelerate the process, such as heating the soak solution to near boiling temperatures or adding another chemical. This appears to be what Noram Ventures is claiming. One process they've tested used a combination of heat, hydrochloric acid, and table salt. Noram's test process extracted 95% of the lithium, which is better than the 40 to 60% lithium extracted by typical brine and hard rock processes. With all that said, Noram didn't explain the steps before and after the lithium extraction process, like whether roasting was used. So, take it with a grain of salt. I'd be curious to know what the extraction percentage would be with just heat, salt, water, and no acid. Even if the extraction percentage is relatively low, the process would be extremely low energy compared to a roasting process and could be lower cost despite the lower extraction rates. That is, Heating water to boiling and extracting 15% of the lithium would be better than roasting the clay to 1000 Celsius and extracting 30% of the lithium. The next step would be to clarify the soak solution to remove the clay with a chemical deflocculation step. This would again leave us with clay for remediation and a solution of metal salts for the extraction step. The extraction step would use DLE to pull the lithium from the solution. This would again leave us with two solutions. One solution that contains mostly table salt, and a second solution that contains lithium chloride. The solution that contains mostly table salt could be recycled back into the process and combined with more lithium clay in the soak stage. This fits with Tesla's claim that all the elements are reusable. As for the lithium chloride solution, in this process, the extraction would stop at DLE and there would be no chemical extraction step to precipitate the lithium chloride from solution as lithium carbonate. The lithium chloride would be piped directly to another process for the next step, which is conversion to lithium hydroxide by membrane electrolysis. Membrane electrolysis appears to be what Vulcan Energy is doing in Europe, and from the few papers I've found on the topic, it seems feasible. In the last video, I said that if Tesla got into lithium mining, it wouldn't save them much money if the lithium and lithium hydroxide production were two discrete processes. This is because mining doesn't require the advanced skill set that lithium hydroxide production does, and therefore lithium hydroxide is where most of the profit is for mining companies. However, I also said that if Tesla owned their own lithium mine and produced the finished lithium hydroxide, it would allow Tesla to design an end-to-end process that might allow them to save more money on the process as a whole. That's what I see when I look at the interlayer exchange process I've just laid out compared to hard rock sources that are usually used to produce lithium hydroxide for Tesla. Let's look at a few key points. First, hard rock lithium is usually concentrated to 5 to 7% lithium oxide before being shipped to the lithium hydroxide plant. After taking into account conversion from lithium oxide to hydroxide, this means it takes roughly 10 truckloads of 5 to 7% lithium concentrate to make 1 truckload of 99% lithium hydroxide. If you're going from North Carolina to Texas, that means large transport costs and CO2 emissions. Second, once at the hydroxide plant, it takes large amounts of heat and chemicals to convert the lithium concentrate to lithium hydroxide. With the clay interlayer process I just described, everything would be done on-site with a fully vertically integrated process that doesn't require heavy transport, energy usage for heat, or chemicals. Furthermore, if the output is lithium hydroxide as a liquid, they could also build a cathode plant on-site and pump the lithium hydroxide solution next door. This would save the chemicals and/or heat normally required to turn the lithium hydroxide liquid into a powder. That is, Tesla may be able to do with lithium mining and hydroxide production what they've done with everything else they bring in-house. Eliminate unnecessary steps and expense by designing a process that unifies processes that are fragmented across several suppliers. If Tesla does decide to go with full vertical integration at their clay mine, it would mean 2 separate battery materials complexes within North America. Given that we can expect at least 1 terawatt-hour of battery production in the US, I don't think this is far-fetched, and to me, it makes more sense. This is because it appears the facilities at Texas will be set up to process lithium from hard rock sources like Piedmont Lithium. Processing materials from a clay mine would require retooling or setting up separate facilities from the hard rock processing. At that point, Tesla may as well just build those facilities at the clay mine. Complete vertical integration from lithium in the ground to cathode production at the lithium mine is a moonshot idea from my perspective. If this does eventually happen, it would be later in the decade. The interlayer exchange process does leave us with an obvious question though. Tesla would be putting a lot of effort in to create a brine and then extracting lithium with a DLE process. Why wouldn't Tesla skip all that and go directly to brine? My only guess here is that it could have something to do with the additional environmental risks associated with DLE brines. DLE brines have potential waste disposal risks and hydrogeology risks from extracting and reintroducing millions of gallons of water from underground sources. A clay resource just has the waste disposal risks of reintroducing clay back into the environment that potentially contains excess salt and chemicals like alum. The amount of remediation required on the clay would be fully dependent on Tesla's process. If, as suggested, the elements used in the extraction process are fully reusable, this is a good sign that the clay waste might be relatively free of contaminants and require little remediation. In summary, I've provided two potential flow sheets for Tesla's process. The first process consumes lithium clay, where lithium is held in the framework layer. It would use conventional tools and processes that are chemically and energy intensive, and therefore expensive. The second process consumes lithium clay, where the lithium clay is held more loosely. It would use cutting-edge technologies, would require a specific type of clay deposit, and would be higher risk. However, the process would consume small amounts of energy and chemicals, resulting in lower production costs. Both of the flow sheets I've suggested in this video were thrown together with a very cowboy approach. They're held together loosely with assumptions and use processes that might not fit together as well as I've suggested. The odds are that Tesla will use some combination of the two flow sheets I've suggested and will include processes or tools that I haven't even thought of. With that said, nothing I've suggested today is new to the mining industry. In my view, for Tesla to make lithium clay viable, it's a matter of finding the right deposit, matching it to the right set of tools, and taking risks with new technology in places where it makes sense. Tesla has the tools, skills, and resources to do this, which means it comes down to whether Tesla wants to do it. Whether Tesla wants to do it, in my estimation, comes down to two open questions. First, does Tesla have confidence that lithium producers will be able to supply them with enough material at the right price over the next decade? I don't think anyone is in a position to know this, but we do know that Elon has an extreme aversion to being under the thumb of suppliers. Second, does Tesla see an opportunity to fully vertically integrate from lithium mine to cathode factory at the clay deposit? Without knowing exactly what process Tesla is using, it's hard to know. As I've illustrated in this video and the last, lithium production is seen as having two broad steps: lithium mining and lithium hydroxide production. Lithium hydroxide is where the biggest opportunity is, but there may be huge cost savings with integrating the mine and hydroxide production that are buried behind these numbers. If I had to take a guess at the likelihood of Tesla actually setting up a lithium clay mine without a partner, I'd put the odds at 70%. Why only 70%? I believe Tesla fully intends to set up a clay mine, but Tesla doesn't shy away from changing their strategy as circumstances change. I don't expect the clay mine to be up and running until 2025 or later, and a lot can happen with the supply chain between now and then. In the next video, we'll look at Tesla's structural battery pack. Again, not my area of expertise, but I should be able to shine some light on what the structural battery pack is and how it works. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video, or snag something off the merch shelf below. I'm also active on Twitter and Reddit. You can find the details of those in the description, and I look forward to hearing from you. A special thanks to Ulf, Clayton H., Lawrence B., Chris Hopkins, and Adam Cezirek for your generous support of the channel, my YouTube members, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.